Welcome to Module 2, Check Sample Measurement and Detector Calibration. During this module, we will be using an alloy instrument.
Niton analyzers are capable of the highest precision and accuracy of any portable XRF analyzer, bar none. However, in order to maintain this precision and accuracy, you have a part to play. Your job is to verify the instrument performance on a daily basis. To do this, a reference sample is supplied. The reference sample will check both the functionality and will verify the factory calibration.
To follow along, please grab your analyzer and make sure that it is powered on. You will want to allow a few minutes for stabilization. Once your analyzer is stabilized, we will want to verify that you are in the proper mode. From the main menu, you will press the mode icon. At this screen, you will see your application icon is highlighted. As you can see here, only the alloy icon is highlighted. If the alloy icon is not highlighted, you will want to tap the highlighted icon, which will take you to a submenu where you can select your application. For the purpose of this demonstration, we are using an alloy instrument. Once we tap the alloy icon, you will hit Chemistry and then All Alloy. You are now ready to verify your instrument's performance with your check sample.
Here we see examples of two different reference samples, one for the ROS application and one for the alloy application. To make it easy to reinsert the alloy sample, make a small slice across the top of the bag, and then you can remove the sample for immediate measurement.
It is now time to take a quick verification test. As we have noted, we are using the alloy application, but the same process applies to all applications.
First, we need to discuss a very important subject, radiation safety. Never point the instrument at yourself or at someone else. Be sure to read and completely understand the radiation safety section of your user's guide before attempting to operate this device. Additionally, some countries or jurisdictions require operator training before allowing them to use the analyzer. Some jurisdictions require licensing, permitting, registration for either the company or the user. If you have questions, please contact your local Niton Analyzers representative.
For specifics on each check sample procedure, please refer to the standard operating procedure and/or documentation supplied with your instrument, or contact your local representative for further assistance. We are now ready to test the check sample. To do this, you will place the nose of your instrument on your sample. For alloy, this will be for about 20 seconds. It is very important to note that for radiation safety purposes, you must never hold your hand over the sample. Note the display, as shown here, indicates the elapsed time. You must keep the trigger pressed during the entire measurement. Watch the screen elapsed time and hold your trigger for approximately 20 seconds. When you pass the 5-second mark, you will hear a beep. This indicates that the normal measurement time for routine sorting of unknown alloys has been reached. Ignore this beep and continue to hold the trigger. Now it's time to check the results. You will be looking at your analyzer screen, but we are going to send the analyzer screen data to our computer for ease of viewing. The data from our screen is sent to the computer by use of the RS-232 cable provided, or alternatively, by use of the optional Bluetooth wireless technology. The software for this is located on the NDT CD. If you prefer to load the software and use your NDT remote viewing feature for this section, you will need to stop this video now and follow your NDT user's guide.
Before we look at the results, let's talk about check samples. Some applications, such as the plastic mode, include factory values for the check sample. This information can be found on the standard operating procedure for the ROS application. Note that your check sample may not necessarily be the exact same lot number as the factory check sample, but it will be the same alloy. For example, our sample has a chrome value of 1.16, whereas the factory value is 1.12. Our moly is 0.48, whereas the factory value is 0.46. For this reason, you will need to document your high-low ranges for your sample on your analyzer for future reference. Okay, we're going to review the check sample measurement results, but we're going to give a little information about the check sample first. Let's review the results screen. Here we see on the top line sample number 780 taken in the all alloy mode. We see our navigation and tools menu. We see the measurement time, 23 seconds. To the right of that, the battery indicator. The identification of the sample, 1 1/4 chrome. Then the element table, the symbols on the left-hand column. The percentage readout in the center column. And the 2 sigma standard deviation, or the precision of the measurement in the right-hand column.
If your analyzer correctly identified 1 1/4 chrome half moly and the values of the major alloying elements are close to that of the certification data sheet, your analyzer is ready to go. By close we mean, if you multiply your standard deviation by 1 1/2, this will give you your maximum deviation value. You will then add and subtract this number from your certified value. This is your minimum and maximum range of measurement result. For alloy reference samples, you will only check the chrome, manganese, and moly values. We do not verify iron since it is only specified as the balance. We also do not include the copper concentration in our normal calibration evaluation, as it is too low for reliable detection in 20 seconds.
We've entered the reference sample results into this table. This is from the last measurement. This will allow us to provide an example of the measurement results. We see, for example, the element chromium is certified at 1.16, whereas we measured it at 1.11. However, we see the precision for 2 sigma was plus or minus 0.7. When we multiply that by 1.5, we get approximately a 0.1 maximum allowable deviation. When we add and subtract that to the certified value, we establish our lower and upper limits, and we see that the measured reading is within those limits. The same thing is true for manganese, which is certified at 0.5. We measured it at 0.49 plus or minus 0.9. The maximum deviation, 1.5 times 0.9, is approximately 0.15. Our lower and upper limit, 0.35 to 0.65, are reading within the limit, no problem.
The moly, however, is certified at 0.48%. We measured 0.54% plus or minus 0.2%, which multiplied by 1.5% is 0.3%, establishing 0.45 to 0.51 upper and lower limit. Our reading of 0.54% falls about 0.03% above the upper limit, indicating the possible need for detector calibration.
The reason I say possible need is that there is one other source of error that needs to be considered when evaluating such a close call.
As you will see from the certificate that comes with your check sample, the moly value includes an error of plus or minus 0.01%. If we add this to our low and high value, we will now be within 0.02% of the expected upper boundary value for moly.
In a case like this, where we're so close to the decision value, even a rigorous lab quality XRF analyzer would be judged as close enough. However, we will perform a detector calibration in any case, as it is simply good practice to do so on a daily basis.
This daily calibration will help prevent minor amounts of electronic drift from affecting your measurement results. In addition, some modes, such as lead-based paint, will require you to do a detector calibration each time you turn your instrument on. We are now going to show you a detector calibration.
I'm going to take you through the detector calibration now. Because we're hooked up via Bluetooth wireless, we'll perform and show the results on the PC. From the results screen, we select the navigation menu. From the list of options here, we select the main menu and then utilities. From the utilities menu, we select calibrate. From the calibrate menu, we can select the calibrate detector option. This initiates an automated detector calibration update that will take at least a minute, but up to several minutes depending on your exact analyzer model and age. You may want to pause the DVD until your calibration is complete.
It is important that you know not to place your instrument near a CRT monitor, like a TV or a computer, during the detector calibration process. You will also want to avoid any source of loud noise or vibration. We do recommend that you place your instrument in a quiet place so that it is not disturbed during the calibration process.
During the detector calibration, the analyzer will show this screen. At the conclusion of the detector calibration, the analyzer will display the results as shown here. A good diagnostic indicator of detector stability is the degree of change of the detector resolution value. We recommend monitoring this value at the conclusion of each detector calibration. If this value goes beyond the plus or minus 20% range, contact your nearest service center for assistance.
For this reason, you will want to record the values of resolution from the detector calibration that you just performed. This will give you the initial value for future comparison. Let's take a look at the values of resolution from the detector calibration that we just did. We see it is 180 eV, or electron volts, the standard unit of measurement for detector resolution. 20% of 180 is plus or minus 36. This will give you a lower limit value of 144 eV and an upper limit value of 216 eV. Any computed resolution value outside this range may indicate a problem with the detector, and you should contact your nearest Niton Analyzer service department.
This screen shows the result of the remeasurement of our check sample. As we can see from the results for each element, we are now within the boundary conditions that we established previously, including the Mali reading, which is now within 1/100th of the upper limit, when we include the 0.01% error from the certificate. If your check sample reads correctly as well, you're ready to test unknown samples.
This is the end of Module 2. Module 3 will cover the measuring of unknown samples.